to do a quick tutorial video on utilizing Smiles code for importing molecular models from ChemDraw as well as from PubChem into molecular modeling software to translate really a one-dimensional code into a three-dimensional code or a two-dimensional code into a three-dimensional code. So Smiles code stands for, it's actually an acronym. Smiles is Simplified Molecular Input Line Entry System. And so this code is a standard way of representing a chemical structure using a simple text string. This allows computers to easily read and understand the molecular arrangement of a compound. And so it's line notation for describing a molecule using a series of characters that can be interpreted by chemistry software. For two-dimensional, such as ChemDraw, or three-dimensional, I use Chimera X, which is freely available from the University of California at San Francisco, as well as Molecular Operating Environment, or MO, from Chemical Computing Limited in Montreal, Canada, right? So for the first thing I'm going to do to get my Smiles code, let's actually look at a simple way, and I've got a simple molecule in ChemDraw right here just to illustrate Smiles code. And so this is just hexane, and in hexane all I have is 1, 2, 3, 4, 5, 6 carbons, and all I'm going to do is model this in ChemDraw. And then I select the molecule with the selection tool. And to get the Smiles code, all I have to do is come up to Edit, Copy As, Smiles. Now I've saved that screen and I can cut and paste this anywhere, right? Now I can come to a molecular editor, such as Mo. Mo is commercial software. I can go to the builder. Now the easier way to actually import, to get hexane is just to use the, there's methane, and obviously then I can just add a carbon, and so there's hexane, right? But to demonstrate Smiles code, right underneath here, see where it says Smiles or ID? I just cut and paste the Smiles code. Now the Smiles code for hexane, it's a single line. It only contains carbons, right? And of course there's no hydrogens included in that Smiles code. And then I just press the smiley face. It wants the Smiles code to be the name of the object it creates in Mo. I'm just going to change that to hexane so it's more human readable. And there's my Smiles code, right? And from there, I can do whatever I want with it. I can add and parameterize a force field. I can perform energy minimization. I use a gradient of 0.01. That minimized very quickly because it's just a single chain, right? I can also run molecular dynamics on this. Now, Mo can handle NAMD for really large simulations. I'm just going to do a very quick simulation using the amber force field that I've parameterized with this molecule. And we can just kind of see the jiggling and wiggling of the atoms a little bit. And there is our hexane in a molecular dynamics simulation, right? And so that kind of shows us how the molecules are moving around. And so then we can stop that. You'll now see that I've certainly moved some atoms around a little bit, right? And so it's not perfectly linear because some of the bonds have been rotated. Now what I can do is I can change this to a space-filling representation, and then, there's my space-filling. And if I'm in a space-filling representation, I can certainly print this. If I go to Render and Setup, I can save this picture as a PNG file. I can also save it as an STL file if I wanted to 3D print this molecule. So STL is a stereolithography file. What the STL file generation does, it looks at the whole surface created with the space-flung representation. It puts little tiny triangles around each atom. And so this quality slider, if I'm at 0, the triangles are pretty big and the resolution is not very good. If I'm at 6, the triangles are really tiny and the resolution is very good, but that can also increase the size of my STL file, and it can also increase printing time and resolution time. I usually set it about 4, and that's kind of a good medium between the two. And then I'm going to do an STL file. I just hexane.stl. I usually don't do, you'll notice I didn't do anything with the scale. I left that because I scale this in Cura or IdeaMaker to make the scale, to scale it to whatever I want, right? So I don't mess with that. So there's hexane, so we imported that directly from ChemDraw. The other thing what I'm going to do, let's go to I'm going to go to Google and let's do something a little more complicated. So here I'm going to do a search for PubMed, or oh, it's actually PubChem, close. PubChem is a database of a couple million compounds, 119 million compounds to be exact, right? They've got a lot. They've got drugs. Here's aspirin here. You can actually search by SMILES code. You'll also notice we have an INCHL. INCHL is also a single line input language. It's very similar to SMILES. It was developed after SMILES code by IUPAC, the International Union of Pure and Applied Chemistry. And it's a little bit more standardized, but many people also think that SMILES is a little bit easier to read. So if I just kind of click on this link, I can actually search by SMILES, and that structure is benzaldehyde, right? So you can see the benzene rings, the carbon's connected by double bonds, and then there's another carbon with a carbonyl on the end, so you can put the oxygen there. What I'm going to look at for is ATP, which is the molecular energy molecule in biochemistry. That's adenosine triphosphate. And so if I do a search for ATP, well, that's not ATP, that's ethanol. The second one's ATP, so there's adenosine triphosphate. I can click on this, and of course I can look at structures. You can actually download the 3D structure. You can download the coordinates in a number of formats if you wish, so SDF or what have you. But you know, the easiest way, because some of these, it depends, some of these are kind of specific. I think the best way I like to do is just to get the SMILES code, right? So we can come down here, compound descriptors. Here's the IUPAC name if you're interested in torturing yourself. Here's the INCHL code, the key. Here's the SMILES code, and I can just copy that. Just highlight it. Control C will copy that SMILES code to the clipboard. And then let's go to my Mo file. And we go to Builder. We go to SMILES, and I hit Control V. There's my SMILES code. Here's where the name, it wants to put the name with the complete SMILES code. I usually highlight that and make the name a lot more simple, right? And if you look at the sequence viewer now, the name is ATP, so it's a little bit more friendly. And so here's our ATP molecule, right? And Let's go ahead and just center that so we can look at it. Now, so here's the ribose subunit. Here's our adenine over here. And then here's our phosphates. Now, if you notice something unusual about these phosphates, these are all protonated. So this is actually the acid form of ATP. And if you remember from biochemistry, the pKa of those oxygens is like 1 to 2. It's very low, right? So at physiological pH 7, those oxygens are deprotonated. So let's go ahead and now if I want to select the protons, I use Shift. I hold down the Shift key so I can select multiple atoms, and we're just going to just delete those protons, right? Now, so if I turn my force field on, I've got to fix hydrogens and fix charges. So now when I look at my force field in Mo, as soon as I fix hydrogens, they're going to be back, right? Because I just deleted the hydrogen. I did not change the ionization state of the oxygen. So Mo is still expecting the oxygen to be deprotonated, right? So in order to do that, what I have to do is go ahead and select the oxygens, and it's just the ones that have hydrogens on it. And then do you see in the 5th row in your builder where it says -2, -1, 0, +1, and +2, this changes the ionization state. And you'll notice right now it's at 0, so it's expecting that oxygen to be protonated. That's highlighted in blue. I want to change this to -1, and when I do that, the hydrogens are now disappeared. Then I can then parameterize my force field, and then I can perform energy minimization, or I can do docking, or whatever I want, right? And so as soon as I perform that energy minimization, you notice I formed an internal hydrogen bond. Of course, I did not have the magnesiums that are usually complexed with ATP in this case, but that's no big deal there. So the protonation state, what you do want to consider, especially if you're at physiological pH, you do want to consider that protonation state when you're importing from databases, because that's a very important step, right? Now the other thing we can do is we can look at Chimera X, and we can also import our ATP molecule into Chimera X. This is a free molecular viewer. Now it doesn't have all the editing capabilities of Mo, but if you're looking at simply importing a molecule, you can import directly into Chimera X right here, right? And so in the command line down at the bottom, you just type open smiles, and then you're going to Control V and copy your smiles code for whatever molecule you have. This is ATP. And then hit enter. And again, there is my ATP molecule in Chimera X. And again, what you will notice is that the phosphates are all protonated. We removed those in Mo, but I did not remove them in Chimera X. Chimera X still had those present, right? So that is that's the one aspect of this. So I hope you've enjoyed this tutorial. I hope this you find this helpful. You can kind of like and subscribe if you find these tutorials useful, and then that kind of helps us out a little bit. So yeah, have a good day.